Welcome to the last lecture of 1645 VNAV. Starting from next week, we're going to have the final presentations for the project. Today, it's my great pleasure to introduce Hayk Martiros, who's leading the autonomy group at Skydio. So the team work on robust approaches to computer vision, deep learning, linear optimization, and motion planning. A bit about Hayk himself. He did his undergrad at Princeton, and then he did his master's in robotics at Stanford. I think he quickly joined Skydio early on, probably, right?
Yeah, right after my master's.
So it's clear that what we do in the class is highly relevant to Skydio. So this is a great opportunity for us. As I said before in the lectures, this is also a great time because they just launched the Skydio 2 last month. So we're going to hear a lot about that. Just final thing, there's going to be a similar talk in CSAIL on Monday. So if you have a friend that couldn't come to this talk, please spread the word. I'm going to share the flyer as well on Stellar. With that, let's welcome Mike.
All right. Yeah, thank you. I'm really excited to be here, in part because this class is like the most relevant background and content you could possibly have for the type of work that we do. And so really excited to sort of talk about that stuff. And I'm going to try to focus on maybe things that are challenges for us currently and are kind of closing the gap between all the things you learned in this class and like what we've been working on to try to put these things in production and make them work. I should also mention I'm here with Alvin Sun, who's an undergraduate who's been interning at Skydio for the past 6 months, and he's fantastic and will be around after this if you guys want to sort of talk about whatever. I'll also say that I almost gave this lecture with a giant mustache, which I was saving up to show to my 5-year-old nephew, but he just said, get rid of it. So there we are. Okay, I'm going to start off with, we can pass this around. So this is the Skydio 2 drone that we're just shipping now. You can take a look. And then I'll start with just teasing you with the first sort of little bit of our launch video, which I'm hoping some people haven't seen, but it's pretty funny. That's enough. You can watch the rest of it too. I'll say just a little bit about the point of the company. So the point of the company is to make vision-based autonomous drones that are trustworthy and reliable and can do things in the world. And I think this is not a new idea. There are tons and tons of use cases for having something that flies around and senses things, but the technology hasn't been there, and that's been our focus from day one, is to figure out how to build up a technology, and that includes the hardware and the full thing. The reason we make the hardware is because having the full integration of everything is really critical to making it really work. And so not just for capturing awesome video content like we've dominantly focused on the consumer side, but also for mapping and inspection, especially of dangerous and costly infrastructure like bridges and cell towers and pipelines, but also rooftops, and anywhere from construction to mining to journalism. Like it's a useful technology, and we're trying to make that happen. Okay, yeah, and it's a very clear pitch. Like we don't have to try very hard to sell the promise of it to industries. It's there. These things are ready for prime time. These types of robots, like we're really getting there. Here's just a couple of example videos of what that kind of thing can mean. So on the left is sort of very close inspection of high voltage power lines at a power station, which is very difficult to do otherwise. On the right is literally being like inside of the bottom of a bridge, inside the trusses, where you're surrounded by metal on all three sides. So there's lots of obstacles nearby, and GPS won't work because you're kind of shielded all around. And then we have this other product that is, we just announced, that is like kind of really exciting, we think is maybe the future of how these things are going to go, which is essentially just a box, a cozy little nest for the drone, which is weatherproof, and it just pops out and then it takes off. And the idea there is it can do a fully autonomous mission and come back and go back in, and it can do this once a day, or once an hour, whenever, and just have coverage over an area, and it becomes more like a software platform that you can run things on than a physical drone. You have to worry about the obstacle avoidance and the flight dynamics and things like that. So that's where we think we're going. Okay, so I'm going to talk a little bit about this clip and sort of how this is done. So this is just a shot we think is pretty cool of just filming a biker going downhill, and this is primarily from visual tracking, and we think it looks pretty cinematic. We're in front of the person, and we're going through some tree occlusions and handling that pretty well. So this is from the main 4K user camera that's on a 3-axis gimbal in the front. So there are 6 navigation cameras if you look at the vehicle. So they're kind of in this delta configuration. There's 3 on top and there's 3 on the bottom in an inverted triangle. And each of those, so this is 1 top camera and 1 bottom camera. And there are these really cool 200-degree fisheye cameras. So they actually see past the horizon line on both sides, which means that the top 3 basically get trinocular coverage of the upper hemisphere, and then the bottom 3 get trinocular coverage of the bottom hemisphere. And so we can still see in full 360 in every direction at once, without needing sort of perimeter guards and cameras on the outside, which are really bad for a number of practical reasons. So this is the same scene of the same biker, and can see because of the wide fisheye, like there's a ton of distortion. The scene is upside down in parts, but this is the raw data we're working with and what everything comes from. Also, I should say, please ask lots of questions. I'm mostly just going to show videos and hope you ask questions. Okay. So here is what that same scene looks like with the navigation cameras put together into a 360 view. And so the yellow border here is showing the field of view of the user camera, and it shows like just how narrow part of the scene it is and why it's so useful, especially when you're flying sideways or backwards, to have that full 360 coverage. Just that broad awareness makes it much easier to plan a better goal. So we make very heavy use of that. And then here is a sort of composite depth view of that same scene, which can be thought of as kind of the output of all of our mapping algorithms. Okay, and then here's one more view of that same thing, which is essentially an instantaneous point cloud as we rotate around. So these are, again, purely computed on vision. This is the path of the biker, and this is the path of the drone. And then these points are just colored by the average intensity in the cameras for that raised projection. And then it's going to switch to being colored by range from the vehicle. It's kind of an instantaneous snapshot of what we see around us.
So, as a quick question,
yeah.
Because of the configuration of the cameras, I guess the horizon will be like in the most distorted part of the image, right?
Yeah. Exactly.
Doing something fancy in terms of distortion calibration there.
Yeah. I'll show some things about calibration, but that is a pretty fundamental challenge here. Is that how we're designing the geometry of the vehicle to get the right camera coverage in the right places. In this case, meant what we ended up with is, like, if the drone is hovering and you're trying to look at something which is near, your horizon, then it's going to be right at the edge of all the cameras, and we basically just tried to tweak their angles and stuff to maintain reasonable coverage, and do a lot of the work through just distortion and careful mapping of which parts are valid and which parts are invalid. But it is difficult, but it's the best kind of compromises we could come up with. Yeah.
So after all your undistortion, how big of the field of view do you have to work with after you've gotten rid of all the invalid pieces and components?
Well, so there's 6 cameras, and they have different invalid sort of parts. So for example, if you get the vehicle, it's kind of interesting. This is the battery up here. This is the motor, the propeller you can see. As long as this. This is the other propeller and the other camera. And that's the gimbal in the front that's moving around, actually. And these 2 things are the protective fins. So if you grab this for 1 sec, these fins here are for protection. If you put it down, and they actually, show up in the image. And but between all the different cameras, like here is kind of showing a really basic form of that, but you do get coverage of every direction, at least with with some number of cameras. Okay, so talk a little about, so state estimation is kind of the most core thing, just estimating everything about the drone. And I think you guys have gone through kind of a visual inertial odometry pipeline and the fundamentals of SLAM. So we're definitely doing that and estimating the pose of the robot as it flies in the scene. We also have accelerometers and gyroscopes, and we estimate those biases online. We also have poses for all the cameras. So in particular, we have CAD for the cameras. We need to calibrate them in the factory because they tend, everyone is different in rotation a little bit, but still, after that calibration, things change a lot, especially because of temperature. The magnesium body can expand and contract, and other factors like jostling or getting compressed can change that, in particular the rotation. The translation doesn't matter much, but changing that rotation dramatically affects things, because the depth perception, when we're comparing between images, it is inversely proportional to the range of the object. And so if we're talking about something that's 20, 30 meters away, it's kind of fractions of a pixel can make a big difference, and that's small fractions of a degree of rotation. So basically we estimate that online jointly as well. Not only that, we estimate the distortion model of the camera that we use to go from 2D to 3D online as well. And that seems kind of crazy until you watch this video. And this is just a fixed camera undergoing a temperature change, and these concentric circles are fixed. So if you look up there, you can see just how much motion you can get of just the intrinsic lens parameters from that. And so that, again, matters a lot, and we calibrate those online. And then, of course, we estimate the speeds of the propellers, which is kind of a lower level thing, and then the gimbal. So because the gimbal is on 3-axis system, and we have sensors on it, but we also, it's on a mechanical isolation system, and we actually also use vision to estimate the exact correspondences between the user camera and the navigation cameras. Okay, so I'll probably skip through a lot of these, but essentially we do SLAM. We track things in the cameras, and we try to solve for their locations in 3D along with the poses of the robot, and minimize the residuals of the projection of the landmark's location through the camera model, the intrinsics and extrinsics, into through the vehicle's pose and compare the pixel coordinate it projects to the ones observed in the image. Yeah?
Is the video from the user camera used in navigation?
The user camera is not currently used for SLAM purposes. It's heavily used for tracking and detection purposes. Okay, so yeah, so there is an optimization problem that looks something like this, where you have a backbone of poses, you have biases for your inertial sensors, you have camera calibration parameters, and you have landmark locations, and we try to solve all this jointly. And the reason we do it jointly is because it works better. It makes more things observable about the system. Okay, here's quick visualization of just some points being tracked in the bottom here, and solving for a trajectory on the right. Again, the interesting thing about the SLAM systems, because we have full 360 coverage, like we can pick and choose. Like if there's some really difficult object, a textureless region, we can just ignore it because you don't need much coverage to do that estimation. That's going to be the opposite for mapping purposes for obstacle avoidance, where you need to focus on every region and make a conclusion, because saying we're not sure is pretty hard to work with on the planning side. Another thing that is an extra complication is, yeah.
For the upward-looking cameras, so the time if you're outdoor with the sky,
yeah.
These will be all outliers for like motion estimation. Are you just having runs like these carvings, or you are into something else, like not too big features on the clouds?
Yeah, so the clouds can still be useful for orientation, but there's definitely heuristics in play for having a selection of features that is a good balance. So if they're all far away, that's going to be an obvious problem and become ill-conditioned. If they're all very close, it's kind of a dangerous game because you're risking losing them all. It can be harder to track them. And definitely there is some, you can have a basic intuition like, oh, the top is usually the sky, so maybe we should have fewer features there. You can also think about getting fancier and actually using semantic segmentation or things like that. Yeah, different ways to tackle the problem. I think there's no right solution other than just iterating for whatever your application is. Yeah?
Well, from what you've said already, I see that probably you're parameterizing the features with inverse depth, since you're using the points in the clouds for orientation estimation. My question was more like, do you only use geometric constraints, as in reprojection errors, or do you by any means use photometric errors?
So that's kind of a tough question to in the SLAM system as I just described here, the residuals are in the space of pixels and are not, it's not a direct approach. We have done that, and we use direct approaches for other aspects of the system that aren't exactly this, but I think the direct answer is they're just residuals in the pixel space. Okay, so these cameras are rolling shutter. That makes things extra special hard because every row is like taken at a different. It's as if you have n cameras where n is the number of rows in your image, and they're all at a different time exposed. And so if you're undergoing fast rotation or even translation close to things, you'll get distortions, and that is really hard to model, but is really important to model. So here we have sort of a bad example here of this car. You can kind of see it jiggling around. And so again, that is well within the realm of causing errors in your estimation if you don't model it. And so typically this kind of jello is caused by a combination of rolling shutter and vibrations in some frequency that makes that line up, and your options really are like get rid of the vibration mechanically, or model it very accurately, meaning know how your camera is vibrating and correct for this. And we do a combination of both. But it can be quite tricky. And even if you don't have vibration, you still have the rolling shutter that's obvious from your scene motion. So if your vehicle rotates or you're filming something moving, you'll get those types of distortions. Okay, so this is one of my favorite slides because it describes what is really hard about vision. So A here is just thin objects, thin branches. So essentially like picking out the signal from the noise. If we're flying fast through a forest and just seeing a thin object and reacting to it, that is the ultimate battle for us. It's one of the things we just focus the most on, and kind of boldly claim that we're the best at it. I think we focus the most on it of any sort of vision system out there, because it matters so much for us. We fly through forests a ton. And it really is a game of like, when can you see it? Like in a single image of a forest scene, it can be incredibly difficult or impossible in many cases that we normally fly to pick out like what is a close object, what is a far object. It becomes far easier if you see two images sort of flipping back and forth, and but even in the difficult cases, even that's challenging. Like it takes a human time to really analyze that and come up with an answer. And our algorithms are like, I'd say, right up there competitively with like close, careful inspection for a couple of minutes, trying to figure out what's going on in the image. So B here is sun glare. Severe sun glare obviously makes things worse, but not only that, in the case of stereo vision, we have essentially a smudge on the lens, and that makes it photometrically very different between the two images. And so I think this is a fingerprint on the lens. It's a good thing to mention. So we handle all this type of stuff by having levels of warnings on the robots. So if we think that a camera is smudged, and we have a couple of ways of trying to detect that, but we'll say, oh, we think your camera's dirty, you should land and clean the lenses, and this is like a warning you can dismiss. Nobody really does that in our experience, and so there's another level of warning, which is basically like, if you're tracking, the drone will stop tracking and basically abort its high-level objective and just hover, and then you have to do something. The reason we don't land automatically is because, well, I don't know, you could be way out over the ocean or something, and that's a bad idea. And so is like automatically trying to come all the way back. So we basically take this compromise and say, oh, you can pilot it manually with obstacle avoidance still, but it won't like do its high-level objective. But anyway, that's what makes this hard, right? So if you're trying to photometrically compare something over here to over here, you're just going to get these like harsh, bright sun rays that don't at all agree photometrically. C is just motion blur. So this, in order to fly aggressively, we can undergo several hundred degrees, like usually 300, 500, 700 degrees of rotation per second. And if we hit something, like flipping over, it can be thousands. And so that becomes an issue. Obviously, reflective surfaces, since we are vision only, this kind of reflective building would look like sort of poles here that are close, and then the reflection of the background would be far away, and so that's a risk for large panels of glass and things like that. What's kind of interesting here is that there's also window blinds you can see as faint horizontal lines. So at some point, like one of them becomes stronger than the other, and you kind of, that's an interesting game to think about. Like you have two valid sort of realities there. And what someone pointed out yesterday, but I don't think we've tried, which is that like if you're flying near mirrors slowly, we should avoid the drone itself, so it shouldn't hit the mirror in theory, but unverified. Okay, E, so textural surfaces, particularly ceilings. If you're close to a ceiling, it can look all white, and that's a bad idea to fly into, versus if it's the sky, then it's a good idea. So one saving grace here is having full 360 coverage, so we can and do actually think about the rest of the scene, and is it more likely to be, does it look like an indoor scene or does it look like an outdoor scene, and that really helps, versus if you just look at the region of space that is just a textureless surface, then it's pretty hopeless to know how far away that is and what to do. And then F is the same, it's close to B, but in this case it's water on the lens, so you can get dirt, you can get smudges, you can get grease, you have cracked lenses if something happened, and all these things will impair performance. Yeah?
For the trees, do you do any semantic detection?
For which trees, sorry?
For the A.
Oh yeah, so your idea is saying like, okay, we're flying and we don't know exactly where the depth of everything is, but we have a semantic segmentation that says this part is a tree, it's probably dangerous, it probably has thin branches near it.
Is that something you do?
Yeah, so the answer to that is it's something we've looked at a good amount, and it makes sense intuitively, but as I'll talk about in a second, like we basically use deep networks for all of our core obstacle avoidance, and they will sort of automatically make use of that information from data. So having the separate system is not really beneficial. Okay, cool. So I'll talk a little bit about mapping. We go to 155, is that right? Luca? Yeah, okay. Cool. So the tough thing about mapping is we can't ignore any picture. Like we really have to just in every direction make some conclusion about what is the likely occupancy of space. So I think, so stereo vision, like the most basic form of how to figure this out, just look for given matches in pixel space, solve for a geometric depth from the camera that resolves given your camera models. And we certainly make heavy use of this geometry with the caveats that they're not linear cameras, they're 200-degree fisheye cameras, so we do lots of work there in modeling. They're also rolling shutter, so we model that, but the sort of core of our system is basically deep learning in the image space, the semantic space, combined with a tight coupling of geometry out to produce maps. And so the classical sort of form here, these are slides from R1, is we have rectified images, you match them, you filter them, you project them in 3D space, and you build a 3D map. I think this is all sort of very well understood stuff in robotics, but the difficult things really come from just like difficult things come here. This is the dominant difficult thing, is just images can look really hard because of all the hard cases we looked at, and then the geometric part is hard because of the subtle calibration change, because of the rolling shutter, because of just any inaccuracies in modeling can be troublesome. Okay, so we published one paper about deep learning that tried to combine a traditional stereo vision pipeline with learning, and we did really well on the Kitty self-driving benchmarks. So this was LiDAR ground truth, this was our prediction. I won't go into details here, but essentially we tried to just emulate the thing where we had, unary towers that computed features the way you'd compute a feature descriptor, and then we made a cost volume, and then we did regularization with 3D convolutions and showed that this worked pretty well and better than just having a monolithic network. This ran at 1 frames per second on a Titan X, which meant we really couldn't use it. The other thing I'd just like to mention is just how much easier scenes like this, like Kitty images and particular driving images, are than our type of images, because of just an enormous amount of regularity. So that's the monocular depth estimation can do a fantastic job on images like this, and because you have a ground plane, you have cars, the vertical distance in the image is very correlated with the depth, and that's the metric itself is like pixel error in the image space, which is just mainly focused on like how accurate is the background to like 1%, which is just completely utterly meaningless for our purposes, for navigation purposes, where we care about like, is there an object that's close that we didn't see, and you really don't care about that 1% margin, and you really don't care about image space, like number of pixels. Your distribution is really like what matters for your action space, which is why sort of like a deep reinforcement learning approach is interesting, because you're trying to learn the perceptual qualities that actually influence your action, which is very, very different than this kind of metric. And also our images just can be anywhere, so there's really not much monocular scene prior that you can use in the difficult cases, because you could be up in the corner of some random room that's painted in a mural and has other objects. So we really can't rely on that. Or in a dense forest scene, like you're just in a tangle of branches and you really don't have an idea from that, which is why the geometry is so important. Okay, so since then, a ton of things have changed, but basically, like, we are running deep networks that predict things. They run about 1,000 times faster than that first one that we had, and I think we were actually, my claim here is we were the first to actually fly a real robot with a deep learned obstacle avoidance system in any sort of substantial way. This was June 2018, and I'll show some examples of what we see here. So this is a forest scene. We're flying through some trees with branches. Here is a 3D version of that. Just a sort of a fused, near instantaneous point cloud. Let's get forward a bit. Okay. So power lines are also real and a big concern for us. So we try really hard to see those. If I pause this video somewhere, let's see. So I'll try to get the same spot here. Yeah, so if we kind of analyze this frame, it's somewhat interesting. So in what we happen to see in this frame, so there's a power line here. You can see it's pretty clear here. It gets pretty faint right here. I don't know, there's, I guess, a small gap here. There is actually one right here that you can maybe kind of just see. It's very, very faint. There's one here, there's two here. So it's you know, they come and go, and again, that signal noise of like, can you see it in the image? And if you can clearly see it in the image, like, chances are that we see it as well. I think in this case, so you can see we see a little bit of this really faint one at the top. That's actually pretty good. And yeah, it seems like we see almost everything here, except for these tiny gaps, which again, the tiny gaps won't matter too much for navigation purposes. But the interesting thing here is like, okay, why didn't we learn to like regularize the rest of the power line from just from the fact that it looks like a power line? And the answer is I don't know. If you ask, like, do we have evidence that there is real semantic like regularization happening where there's no photometric signal? The answer is definitely yes. There are clear cases where we have some magical things happen in terms of just like filling in and making the correct assumptions about things, like a case where we don't even have the other match of another power line geometrically, but we'll still predict something that is reasonably in the correct place and the right shape. And so it's there. And then here's sort of an indoor scene. This is our office, and you can see large sort of textureless region with specularities, and really not much to go on in terms of photometric matching. And we do a pretty good job in these types of scenes. Yeah?
Are you just using one camera and passing that through the network independently for all the cameras, or do you do some joint?
No, we're not just using one camera. We rely on the geometric constraints as well. So unfortunately can't talk about like the exact details of the configuration of things, but in general for our system, like we use both cameras in space, like the trinocular, up top and bottom, and then we also use them through time to estimate things. And they have different characteristics for when it's useful and what.
And the user camera, you never use it for that estimation?
We don't. It is tempting sometimes because there are things we can see in that we can't see in the other cameras. The trick is you're kind of like, it's again such a narrow field of view and we could be looking over here and flying that way. And so anytime it's like we could use it if it happens to be in that direction, but otherwise won't, like it can be useful, but in general is just a tough thing to rely on for that purpose. Yeah?
How do you get your ground truth for training those networks?
It's a good question. So there's simulation, there's real data. The nice thing about simulation is all the ground truth. The not nice thing is it is really hard to make it transfer. You can put a lot of work into that. So for real data, we have tons and tons, like every flight we do internally, we log all the images, we have all of that data, but we don't have any ground truth. And there's lots of ways to think about doing that. Like we've strapped a LiDAR to our drones, we've done offline reconstruction to try to be more accurate and use acausal data. We've tried using basically just unsupervised learning where you just rely on photometric cues. I'll say it again, the photometric cues are really tough because they'll get you the easy medium cases, but the hard cases, I think that's an unsolved problem. So if somebody can figure out how to use unsupervised data to solve cases like just purely unsupervised data to solve the really hard cases where it's not photometric consistent, that would be a real win. So I guess all I can say, like we use a combination of things that we've like built up internally over a long time, but it's a serious challenge that we don't have ground truth for real data. Yeah. Okay, here's another cool artistic one. Just to visualize the depth map. And this is kind of a case where someone just pushed back on the joysticks and the drone kind of like navigates and avoids obstacles. And it's a fun aspect of the product where you just, like you can fly manually, but you don't have to be a pilot and you don't have to really be worried about crashing. You just kind of move around and that's fun.
Quick question. Can
Yeah.
you go back to the previous one? So
This one?
the previous one.
This one.
So how much temporal smoothing or temporal regularization do you have on the map? Because here I see things moving pretty fast and optical is also
Yeah.
pretty fast now.
Yes, in this view, it's essentially just an instantaneous point cloud is what we're drawing. I think there's like maybe 2 point clouds drawn on top of each other and disappearing. So this is like essentially no smoothing.
But after that, you typically pass that volumetric stuff, right? Volumetric filtering.
Yeah, it does go through some amount of smoothing before being used for obstacle avoidance. And this is all like, yeah, there's a ton of stuff you could do to improve these things in an offline reconstruct. If we're actually trying to build a map of this room and not just avoid obstacles, which is something we'd love to do, but not really been our dominant focus. Yeah?
So for planning, how much history does, basically how much history do you keep in the map?
I can't answer that, sorry. Yeah, wish I could. Okay, I'm gonna skip. Here, I just wanted to show one typical example of just a case where in a single image it's really hard to tell what's going on. This is not a particularly rare example. This happens all the time, but okay, it's extra hard to see on the projector, but basically there's a match that's moving from here to here. The bottom is moving from here to here. There's another branch here that's moving there, and then it kind of curves down and disappears into the trees here. It can be really hard to see. And here's the outline of the closest part of it. And then here's another interesting one where we're flying above power lines, and you can kind of see there's one here that's somewhat visible, and then there's another one here that's quite visible but disappears over the ground. I'm just trying to kind of give a qualitative sense of some of these things. Here's one fun trick related to what you asked, which is, so trying to learn about glare, we could take synthetic suns that we generate, put them on real images, and then try to say, oh, well, if you have this sun, you should predict the same thing with and without this sun, even if we don't know what the ground truth is. And that's something neat that kind of can help with making the best of not having ground truth. Okay, so just show a quick video about object tracking. So this is just showing a lot of occlusion lighting changes, a lot of pose changes for a human. The top right is a pixel-wise segmentation of this instance of a person, and you just show it, kind of cool to see the 3D just trajectory projected into the image, which shows, you know, good quality state estimate. And then the bottom right is just a top-down view of trajectories of the drone and the person. So here I'll show, so this is our three founders kind of running in between each other, and the drone's doing a pretty good job of discriminating between them, and tracking multiple people is actually really useful, even if you're just following a single person, because you can discriminate against them, and you have this matching problem, which is basically like, what, you know, where are the people that I see? What is their motion model? Like, how are they moving? And then what is the visual appearance of their body? And then there's a kind of an optimization to be solved there for what are the likely true person instances and tracks there. And this is actually old. This is a lot of what Alvin has worked on and done an awesome job there. So Skydio 2 is actually much better at this than the R1 was. Then here's a fun example of this failing. So basically, one person runs behind another, and then a third just pops out from behind at like in a similar direction. And it's just a clear case where the visual appearance of the body is not enough to outweigh the chance of someone just disappearing and someone else appearing. So that's a clear failure. Okay, and then in terms of planning, I think I'll go very quickly here. Like, we have a bunch of uncertain knowledge of the environment, so there's really no guarantees to be made about anything. Like, we have some knowledge of where we are, we have some knowledge of our high-level objective, we know our map, we try to represent uncertainty in the best way we can, which typically comes from, you know, pixel space matching and propagates through. And we have to basically, you know, think about these different components and how they interact, and putting them together in a simple diagram is kind of the best thing that I could come up with, where we have some state that represents not just us, but the whole environment of everything we perceive. And we have a planning policy that needs to come up with an action, which is, say, just propeller commands to drive the drone somewhere. And then we have a model of how the world will evolve. We have a better model of how some things will evolve, like the drone, than other things like the motion of a person, because they have free will, allegedly. So the most important part of the planning system is to come up with an objective function that captures really what we want. Says, like, what are all the things we care about, and if we can plug in a trajectory of the robot to this and find the minimum, like, that's what we want. And the way to get this is really domain specific based on what you're trying to do, but it's a ton of iteration and building up knowledge and trying things out, and just learning that that's not actually what you wanted, but this will generally capture, you know, like obstacle avoidance and smoothness and your high-level objective, maintaining a track of a person, and not exceeding the dynamic limits of your drone, and a lot of other things. Like, for example, we have a mode where the drone tries to keep a height above the ground so it's safe and doesn't kind of like go down near people, and there's also a height ceiling, and there's just a ton of small things, and they all have to kind of combine together. So we try to model this objective function, and then we need to basically solve it. and you just repeat. That's kind of the process of our motion planner. And there's lots of ways to try to do part 2. You can do optimization-based methods, you can do sampling-based methods, you can learn, and we've tried and actually use a combination of these things. One cool thing to mention is like we do have a core part of like our planning system that is running a nonlinear model predictive control, and that kind of tries to encapsulate as much of the knowledge as possible of the objective function, so it reasons all the way from like obstacles in the scene down to the actual limits of the rotors, and that's really cool because again you can jointly get just the maximal benefit out of your solution rather than having separate components that do different things and have their own limits and have kind of an interface that is not perfect in their assumptions. Okay, we use lots and lots of simulation. So for perception, we can go through thousands of logs and rerun our algorithms and look for statistical results there. For planning, we can't really do that. But the nice thing about simulation for planning is it doesn't have to be very good. So we drive this guy around. He just slides on the ground with gamepad all the time and just see what happens. On the right here is something, we can basically, if we're trying to make some decision like how close do we get to obstacles, we can just generate a ton of scenes with random trees, run a person through the same thing, and then see where the robot gets stuck, how close it gets to things, and just try to gain knowledge. The tough thing about any of this is like, the drone generally works. In the vast majority of scenes, the vast majority of cases, like it does a good job. And so when we see a failure, we can try to fix it, but what we're worried about is making 5 other situations worse. And so really like it's in the statistics of trying to gain confidence that we don't regress something else in order to make progress. Okay, yeah, the other cool thing about simulation is that same thing can be really helpful for building an SDK. So we have sort of this Python level SDK that's still in private beta that lets people drive around the drone, and it basically doesn't let you crash. You can see obstacles, and you can generally do things with the drone at a high level. We also have a mobile SDK, which is like you control our drone with your own mobile app. We're trying to work on those things. The tough thing about it is that it's hard for, like, the goal is to make people who don't know about robotics able to use this thing, but it's hard to build an API that is like elegant and able to be used without sort of understanding what are the limitations of the drone, why can it do this thing and not the other thing. So it's like definitely a challenge that we're trying to work on. Okay, we estimate the wind. This is really useful for aerodynamics. This is something cool. Actually, not really relevant for Skydio 2 because it doesn't have the guards, but we actually can add in obstacles into the map when we detect a collision, in this case for a glass pane, so we don't run into it. And then we focus on recovery behaviors for sure, like this is this inverted pizza toss. This is kind of fun. So we found out that with just parameter changes to our planning system, we can find a mode of like stability to just still hover by just spinning the other 3 propellers. And this is like a known thing. There are papers about this, but it was cool to see us emerge from just a parameter change of saying like, okay, this rotor's shut off. And we also show that we can avoid obstacles and follow somebody in this mode. This is purely in simulation for the record. There's no state estimation working here, but it's cool that it kind of works in sim. As far as the modeling and planning goes. Yeah, that's it. These are my slides from CVPR. Don't work on improving Kitty, please. That would make me sad. And then I'll just put this on. This is one of my favorite videos of just 4 R1s following somebody as he goes down a water slide from 4 angles. And they're not working together here. It's literally 4 phones. We have done more stuff in this direction since, but it's just a fun one to watch. Yeah?
How do you handle physical interaction from the user, or if it attaches a payload, or if it tries to interact with them?
We basically, you're not supposed to attach a payload, and if it's a big one, I think you'll see warnings. If it's something small and it's obstructing the cameras, in a bad way, like we'll try to, that should be detected as like a dirty camera equivalent, but I wouldn't recommend trying it. Yeah, I don't know, it's a scary thing, because like, okay, let's say someone hangs a string with something, does the drone now like just continuously fly up because it thinks something's underneath it? And it might, like that's you know, something we're trying to work on, and it's always tough, like selling a fully autonomous drone, someone buys it, and then we like have this guide saying, please like read this and do these things, but what happens is they're not very trusting for the first 2 flights, and they're like, oh, actually it worked perfectly in my backyard, now I'm just going to assume it's always going to work and never fail and has no limits, and then and of course they never read the instructions, so it's a challenge to like figure that out. Yeah, this is pretty much, this is it. If you guys, obviously we're always interested, especially from people in this class, like I would love to hear from any of you, and we like are doing, you know, internships and hiring, so yeah, thanks for having me here, and we'll be around a little bit to talk to folks if you'd like to. Yeah.